Hi, this is the primer I wanted to give on contextual geometric structures. My name is Bradley Alicia, and there's my website. If you have questions about this talk or about our approach, you can go to that website and find my email and email me. Or if you're in the Saturday morning NeuroSim group, you can contact me on Slack, or you have my email in that case. This talk, I've given a number of iterations of this. This focuses on representational layers for cognition and culture. And so you have a sort of a diagram of the approach here. You have these geometric things that are like 2-tuple and 3-tuple surfaces, and they represent data points that represent sort of a culture. But you also have these population level models that have agents which contain these geometric structures, and they interact with each other and they form these sort of homogeneous clusters. And so it's loosely based on fluid dynamics. We'll talk about it a little bit later. And then this applies to a wide variety of cultural scenarios. So, for example, like a communal village setting with a large urban settlement where you have people interacting massively parallel ways. And you have situations where you have cultural contact, so two cultures that are very different interacting for the first time. So we sort of take a very anthropological approach to culture. So there are two different kind of definitions of culture that I think of. One is sort of the academic or anthropological version of culture, which has a lot of specific definitions, and then there's the popular version of the word culture, which is like pop culture or fashion or whatever. We're going to put that aside and talk about the anthropological definition. And so we're not going to talk about like nailing down a definition. We're going to talk about some of the properties of culture. One of those properties is that culture is based on heredity. So you have a set of beliefs that propagate across individuals, and you acquire them from books or from other individuals. It's both intergenerational, like if you go to school or if you learn something as a child from your parents, and it also propagates across the population. So something like heliocentrism can be inherited from, both from school and from like just, as a popular belief. And then that influences other beliefs, and there's a cultural change there. You also have adaptability. So culture is highly adaptable. So you can, we can do things. We have culture, and we can exist in places where humans probably wouldn't exist if we didn't have culture. So it allows for us to adapt, but it also allows for us to adapt to natural environments, but also social environments. And then self-reference. So there's the ability, so culture is really based on a referential system. And we use references for things. We have stand-ins for things. But we also have sub-references. So we can use certain symbols as stand-ins for objects and use a reference that involves both the object and the symbol, and there's a lot of self-reference, so that's an important factor too. One of the traditions we draw from is structuralism, and so structuralists and post-structuralists believe that structures transcend cultural transmission and cognition, but fundamentally shape the features of culture. So structures are things like politics or religion or urban settlements, where sort of individuals are constrained by those structures. If we want change to happen, we often have to do them within the bounds of that structure, or else change the structure entirely, which is much harder than, say, like acquiring a belief like heliocentrism. So it's very, it's very subtle from our perspective, but if you look at like history, you can see how structures change over time. But structures are also ubiquitous. So, structures are linguistic. They can involve concepts. And one of the things about structures is if you draw your structures from the natural world is interpreted as a set of discrete oppositions. So, you think about like an opposition between light and dark. or an opposition between sweet and sour, or an opposition between dangerous and safe. Those sorts of things are, we take those concepts from the natural world. We have like symbols like, the wolf or the sheep. We think about peace or war, in terms of animals maybe, or in terms of some other set of symbols. And, warmth maybe is the sun, and, or heaven and hell. Heaven is not hot, but hell is hot. And, those are cultural concepts that we have sort of acquired. And of course, in other cultures, they think of them differently, but they usually sort them into discrete oppositions. Structures can also exist in settlement patterns or in architecture. So actually in those cases, it can serve to define or sharpen distinctions between cultural groups. So you can have settlements that look differently, and over time, those things will look even more different because they're different cultural traditions. And so but you can also have syncretism, where you have cultures that come together and form, syncretic cultures. Like, when Europeans came to the New World, they adopted a lot of native traditions, and those things, went back to the Old World and influenced things there. And, there's a syncretism eventually that arose from that. It's a new culture that, resembles parts of both cultures. And so those things are possible too. And so, but structures are, they're underlying constraints in structures, and they basically specify a lot of times how cultures cannot adapt. So like with political systems, political change is not always possible, and sometimes that's due to just the structure that exists. It doesn't allow for certain types of change. You have to change the entire structure in order to get the desired change. And so those are all things to keep in mind. We do take inspiration from anthropology. So structuralism was something that was developed by Claude Lévi-Strauss. This was many years ago, probably a century now. And his argument was that cultural relationships are a series of overarching structures. You can understand them as binary oppositions. You can understand them in terms of kinship and things like that. But structures are the key to cultural representation. And so our relationship with nature, kinship, and the ritual world all derive from those structures. But the post-structuralists, and one of the representatives of that movement was Michel Foucault. And he basically, him and his school, they critiqued structuralism in a number of ways. They thought of signs or binary oppositions as being signs, and that those signs were dynamic. So you have binary oppositions, and in the structuralist tradition, they were more or less fixed. But in the post-structuralist tradition, the binary oppositions were dynamic. And their focus, I think, was more on change and how structures change, as opposed to how structures exist as a sort of a static entity. So, are they universal? Are structures universal? Maybe not, but it definitely is the case that structures change across cultures. And so this is one of the things we think about in this approach. So I'm going to present some examples of sort of structuralist representations and maybe some post-structuralist representations. And we have to keep this in mind when we think about these representations. But it's also influenced by something called the habitus. And if you've ever read Pierre Bourdieu, you know that he has this concept called the habitus, which is very diffuse. It's even more diffuse than structuralism. But it basically boils down to this idea that people have habits, and those habits, sometimes you think of them as psychological, but they can also be cultural. And so when habits in the cultural realm, they're considered to be practice. So you practice things like, you might pray, or you might eat with utensils, or you might, play a sport that has rules, and you might play at a certain time of year or whatever. Those are all rituals, and they're practice. It's cultural practice. And this is embodied behavior that exists. It could be ritualistic. It could just be maybe a little less formal, but these are things that you do on a regular basis. And those things are linked to cultural representations. So he thinks of them as schema. And he also thinks of the social actors as automata, which is kind of a nice segue to a computational approach, because the habitus, of course, wasn't really thought of as computational at all, but it has links to computation. So I always found when I read Bourdieu for the first time, it was very computational, and a lot of people didn't understand what I was talking about. But if you read it, you'll see that there's a lot of sort of covert computation in there. Like it's definitely a mathematical or quantitative cast to what he's talking about, even though it's very dense rhetoric and prose. So all these things inspire this approach. So I'm going to back up and ask a question here. So how does the brain represent sensory information to perform a cultural operation? And I put represent and operation in quotes because those are just kind of things I'm using for a matter of convenience here. So the answer to this is that, and I said like the brain is sort of perception, and then there's a cultural layer, which is different. And so the idea is you're getting sensory information and you're bringing it into a cultural representation, and then you're doing some practice, which is cultural operation. So, I show this stuff here. I show multimodal integration in the brain. And then I show this, this is sort of replicated as the structure. So the structure is actually a two-tuple and three-tuple representation of the thing that's going on in the brain here. And so a two-tuple surface, for example, has olfaction and audition. Okay, and then the three-tuple surface is vision, olfaction, and audition as a three-tuple surface. So these are inputs that exist on these axes. And so something that's an input to the system, which is, maybe like, is something auditory or something olfactory. We can embed this in the surface by asking that question and then giving it a certain membership in each category. So stimulus like me talking, there's no smell involved, hopefully. And there's a lot of audition. And so it would be like 100% in this audition category and 0% in the olfaction category. Now, the three-tuple surface is a little bit different because you add vision in. So now you're watching these slides, you're listening to me, and there's maybe a 50% membership in both audition and vision, but a 0% membership in olfaction, so it would be here. So that's how we classify objects according to this model. And this model, of course, draws from what's going on in the brain. So we use a soft classification scheme, which means that we can take these categories and find some membership within that category. So if something is, mostly visual, we can give it a number. If it's mostly auditory, we can give it a number, and so forth. And so your data points will fall within these surfaces, depending on how much of proportion of each thing that they are. So this is just with like sensory inputs. We can use different higher level concepts to also classify things, represent them. And so cultural phenomena is a symbol, a practice, or an artifact. We can classify artifacts like chopsticks or a mask or a stop sign. We can look at practices like seasonality, or things in relation to seasonality, like it could be planting crops, or it could be if you're playing basketball, you don't play basketball maybe in one season versus another. So we can do these things, and the question is you have to ask is, what is the membership of cultural phenomena X in this space? So we take an object and we can break it down in different ways. And so we can use like auditory, or we can use sensory inputs. We can use higher level properties like, the scariness of this mask. It would be scary, safe, and maybe, some surface property like stone. We have a hypothesis maybe that stone things are scary, but maybe they can also be safe. And we can use stone versus not stone to sort of disambiguate that. So those sorts of things that are possible here. So this is we call well, actually, when I refer to this as a hybrid model, I'm referring to this as the soft classification part, which I just showed you, and then the LCS part, which is I'm using LCS as a stand-in for broader class of these mean field models that I showed you in the first slide. And so you can read more about this in this paper here. This is from 2012, Proceedings of Artificial Life. 2 components of the model that we're basically laying out in this paper. The soft classificatory kernel, which is the thing I just showed you, which is where all phenomena have some degree of membership in these classification kernels. And so, like I said, halfway between light and dark, they would have a membership in both light and dark. And so you have attributes of both. So you think about like a conventional classification system, you would just simply say, is it light or dark? Okay, it's maybe, somewhere in between light or dark. So you would say it's 50%. And then, but then it doesn't ask the sort of the counterfactual question, how much of it is dark, how much of it is light. So this is useful in terms of building higher level representations. If it's light, if you have 50% light, then you might ask the question, is there some other concept we can link to light versus link to dark? And so if the membership, and you can look at a range of different stimuli of different membership, degrees of membership, and ask the question, okay, now, what are the other attributes of these stimuli? And, what are their membership in these other categories? And so, it gives us a way to kind of break apart these, use very general terms or general mechanisms, and then break things down into finer and finer parts. And we can look at some of these references and self-references and things like that. The other thing are these cultural landscapes and integrative communications. So, we talk about the kernels, but those are in a single individual, okay? But then you have kernels across individuals. Those individuals, of course, are going to vary. So we might not want to have a common classification kernel across all individuals, but we might want to vary it a little bit. So, because not everyone has the same experience in a population. So we might want to vary that somewhat. And so now we have these mean field models they're hydrodynamics inspired field models. LCS is a specific approach to this, which I won't talk about in this talk, but it's basically where you put a bunch of elements in a field and they diffuse across the field, and you look at their patterns of aggregation, and those things are based on the internal properties, but also on other forces. And then we're also going to talk about pairwise interactions based on the concept of minimal markets. It's a little bit different approach, but it's something else that's possible. So here's an example of soft classification. This is, again, our 3-tuple surface, and this red line here delimits all the points that we get from this stimulus, which is a car crash. So we're representing this car crash as a series of different sensory inputs. And all those points, they vary quite a bit, but they all fit into the space. So you just observe different points of the car crash from different perspectives, or different, parts of it. Like, if you think about driving past a car crash and you look out your window and you only see part of the action versus another part. So you would sample it multiple times from different perspectives. And given that, you get this area. And so this area then has every element in the area as a membership function. And so there are 3 membership values for each point. So, say for example, there's a point where there's a 80% vision, 80% member in audition, and a 10% membership in olfaction. And so these points don't have to be proportional, and I'll talk about that in a little bit. They can be sort of separated in space, in the sense that your membership is a little bit different. You can have a lot of audition and a lot of vision in something. And so, but these points generally reside in this space, and what you end up with are these cultures. So the limiting thing is a culture, and the cultures can either remain separate, like the one down here, this purple or pink point and this red point. Those two are separate. But if you look at the red and the blue, they're separate except for an overlap region, which is a screen. And so they can overlap to an extent. And so our membership functions create a bounding polygon, which are all possible responses to a sensory stimulus, and where all individual experiences will reside. And these subspaces can be defined by culture-specific, context-specific instances. So we have these, when you have a situation where these things are separate, those are separate cultures. It's a little bit maybe confusing to think about it. We've done some software implementations on this, but it hasn't been clear how this actually gets played out in programming. But I can talk a little bit about how this relates to mathematics and to category theory. So let me kind of get on with that. So there's a soft fuzzy classification. The membership function is on an interval, and it's not a probability. It's this sort of membership. It's a fuzzy membership. And so if you're familiar with fuzzy logic, it may be somewhat familiar, but it's not really exactly the way they did in fuzzy logic. This is the way we're doing it here. But what's important here is that this approach does not require transitivity, distributivity, or symmetry. And so you see what those are. Transitivity is where, if B is greater than A and A is greater than C, then B is greater than C. And that's violated often with these. Symmetry is where A equals B, then B equals A. That's also not always the case. And distributivity is where you have A times B plus C can also be restated in this form, but that's also not always the case. And so our conceptual automata, we have this empty tuple from a 2 to a 3 tuple. We have this represented sort of as an empty space, but then represented with our data points, and you can see that there are different cultures that overlap and don't overlap. And this is the two-dimensional case, and this is the three-dimensional case. So in the two-dimensional case, you have the hot-cold opposition. In the three-dimensional case, you have hot-cold and some other culturally specific label. Okay. So let's see. I go back to the habitus again. I think I put this slide in differently from the other slide, but it's inspired by The Logic of Practice by Pierre Bourdieu. That's the specific book that I think you should read if you're interested in this. It gives you like a pretty good idea of some of those ideas. And he gives a lot of definitions. Like I said, it's very verbose and dense, but he gives a lot of these really intriguing definitions. One is durable, transposable dispositions. He uses the term generative. He uses the term organizes, practices, and representations adaptively. So all those things are like kind of thrown around in the book. And so this is what we're trying to capture with these automata. But there's a more concrete computational objective, and that is that these automata are a scheme that transforms physical phenomena into operations that can be compared in an evolutionary context. So like I said, cultural attributes are evolutionary. They're not the same as biological evolution, but there is an evolutionary aspect to culture. And so this is the thing we're interested in. So one aspect of that evolution is where you have sort of, now you have to kind of think about this in terms of these automata. They're sort of based on this idea of static structures, right? Like talk about structuralism and how you have these static entities. But now let's suppose that you move to sort of a post-structuralist view, or something where the entities aren't static. And so that's what we're talking about with incorporative models. And so this is for rapidly expanding areas of knowledge. So a robot is seeing the Statue of Liberty for the first time. A robot has never seen this before, and they don't know what it is or what it symbolizes. And so it represents a lot of things. It represents, well, first of all, it's a sculpture, which the robot may have never seen, holding a torch. So they don't really know why that is. The robot might expect the statue to move, but also what it represents to people. And so it might represent a wide range of things to people. The robot knows none of that. So the robot has to expand its base of knowledge, both both symbolic and representational. And so this is sort of an oddball cultural behavior problem. So you take an idea that's outside the prevailing wisdom. How do you evaluate it? Is it something that's sort of an outlier, or crackpot idea, or is it something that will eventually transform this prevailing wisdom? So you're here, and this is the prevailing wisdom. You're observing the oddball cultural behavior here, but this is the prevailing wisdom. So for the robot, the prevailing wisdom might be being a robot and being trained on objects in the lab, and then they get released into the world and they see this statue and they don't know what to do with it. Is it just a one-off? Is it something that, or is it something that the robot is going to have to incorporate into its worldview as a part of the world? And so one of the approaches that I took on this a long time ago was this linear scaling approach. So this is using a genetic representation alongside the kernel geometry and using a scaling factor that can adjust these axes in a way that responds to new information. So it refines the axis in terms of its endpoints and the interstitial membership. And so, but that's not necessarily the best approach. I was talking with Jesse Parent. We were talking about information geometry and brought to mind something that I had forgotten. But there's also another way to do this, which is the homeomorphic transformation. So this is where you have your original representation of A, B, and X along these axes. So the ends of the axes are these letters. And you transform this using a homeomorphic transformation. You transform it from X to some other form Y, which is this different geometry. So you have A, B, and X, but they're embedded in a different geometry, and the geometry stretched out. So now you have this different representational space, and it allows for a different type of representation, and it allows for different types of relations to happen within them. This is pretty abstract based on this example, but I think, there are different ways that you can deal with this incorporating new knowledge aspect of it. The idea is that your representation is evolving in some way. And so depending on how you want to set this up, you can make this work more, better or worse. I don't know. We haven't implemented this, but it's a way to think about it. So I wanted to go over membership and sets quickly. And so I talked about this previously, where we have memberships in two sets. So let's take two sets, R and G. And so this is sort of a qualitative representation. There's no, we don't know what it is. But we're just showing this over an interval 0 to 1. So this is 0, this is 1 for both. And so we see that these two sets, and these are separate from what we have in the kernels. This is just setting two sets in a bivariate relationship. So we have R and G. And so we can see that there's a union. There's an intersection of actually the intersection is up here. I have this wrong. The intersection is up here of R and G. The union is down here. And then you have the maximal membership in R and both in R and in G here. So 1 is here, G is 1 here, R equals 1 here. And so you have these different, it's basically set theory, right? You have two sets. But the thing is that a probabilistic relationship, you would have these, basically these isometric lines that would predict P and Q. So if you had an 80% membership in R, you would have a 20% membership in G. That would follow P equals 1 minus Q. And so probabilistically you'd expect that relationship. But in our membership, in our fuzzy sets, we don't expect that at all. We can have maximal membership in both, which is the intersection, and we can have membership in neither, which is the union, or anything in between. And so that's the reason why I've shown this entire space and put this in here. Also, there is an equivalence of membership. So you can have 50% in R and 50% in G, or you can have 80% in R, 80% in G. And so that would be along this dotted line. But in a traditional probabilistic representation, that wouldn't be the case. So membership can be non-communicative or commutative. in some cases, equivocation can equal ambiguity. So in some cases where you have maybe this dotted line or maybe like a traditional probability, it's ambiguous what the full properties of that object are. So there's you're refining your representation by using this type of an approach. So an example, of course, is an object may have a 45% membership in R and a 75% membership in G. And so this is a very basic way to do this with a sort of a fuzzy method or a soft method. There are alternate methods, sort of quantum probabilities are an alternate method here, which is much more difficult and maybe less analogous to cultural systems. People talk about quantum, they use quantum analogies a lot, but I'm not a big fan of that, if only because it really, it is a lot of math to get somewhere where maybe it isn't necessary. And so here's some examples of contextual structures. You have different tuples, so like different numbers of oppositions. You have 2, 3, 5, one tuple, which is where you have this idea of modulation, and then there's pain. So there's like pain or no pain, and it's sort of just a modulation. Then you have these 3 tuples with a contextual anchor. So contextual means fluctuation. This is actually one tuple with contextual anchor. So modulation would be meaning that if I had if I had like pain versus no pain, that's not really a lot of information. There's modulation in that, which is how much pain do you have relative to maybe like the absence of pain. So that's what I'm getting at here. And hot and cold and fluctuation means that, how much is it fluctuating between hot and cold? Is it, you have things that are very, very hot and very, well, you can't really have things that are very hot and very cold, but I guess you could. Fluctuation gives us a means to sort of give a contextual anchor to that. There's a contextual anchor, umami. So in taste, we have these different tastes, and sour, bitter, sweet, salty, and umami. And umami is actually a Japanese word, meaning like some taste in that you find it's common in Japanese cuisine. Now, like given your cuisine, you might not ever experience umami. In fact, you might not ever experience sweet. But umami is a contextual anchor. You have to have the context of umami to really identify it. But you also have the context of salty to identify it too. So these contextual anchors are a little bit hard to, there's a little bit of variation in terms of implementing them. But so this is another example of representations. So we have in this case, goes back to the color representation stuff that we talked about a couple weeks ago in our group. This is like an example where we're just kind of like mapping these different things that you see in the environment, like in terms of color, onto representations. So in this case, we have different colors. So we're using the CMYK space. This is a 32-bit representation. And we're using these colors and we're mapping them onto the space based on 2 attributes. The D, which is sort of a radius, which is present or absent. So it's either 0 to 1. So if it's like at the middle of this, it's 0, and at the edge it's 1. So if it's absent at 0, it's sort of at this origin point. If it's present, it's out here at 1, so it's in this sort of edge space. And then the membership function is actually measured in radians. So is it present or not present? And that can be measured along the edge here. And so we have areas that are C, areas that are M, areas that are Y, and areas that are K. And so we can have like a single observation will have potentially 4 points. One in the C quadrant, one in the M quadrant, one in the Y quadrant, one in the K quadrant. And this is actually, I came up with this example after watching the stuff that Anson showed on his circular representations. And so you can do this you can use a circular representation to represent a lot of things. It could be different attributes of a color. It could be time. It could be other things. This is color sorting and recombination, so now this is called a 4-space. This is CMYK. This is no blend, or CKMY. This is no blend, meaning that these quadrants are separate, and there's nothing, there's an interval here and presence and absence. So we have these intervals that are, independent of one another, but they're in the same circle. And so it can give you information, say, about mapping between the different color components. There are a lot of things you can do with like this sort of 4-space circular representation. The 2-space circular representation, which is this combined CK and combined MY space. So in this case, you're combining the C and the K channel. You're combining the M and the Y channel. It might be like an averaging or some other smoothing mechanism, but you're representing just 2 components of the color. And it's, again, in this interval, present, absent, so it's closer or further from the origin at the center of the circle, and then there's this interval which represents its presence, or its degree of membership in that category. Which is like, if when we use the RGB example in color, if it has a red value of 255, it's totally present as a red component. If it's a value of 0, it's not present as a red component. And so that's how you would come up with the membership function there. And so then you can have this, again, you can have this one space where you're just representing the color, how close it is to, in this case, it's how close it is to any of these 4 components. So, if you think about like where it fits into this space, you'll have, if it's like pure C or pure M, then it's at one of these poles, right? But if it's not, then it's in between. And so, again, you have to take your stimulus and you have to code it in a way that's like fits into the space. But then when you have it in this representational space, you can make statements about how, they cluster and how the representational relationship between things. And there's a metric space inherent in this. Now we move on to this cultural landscape idea. And so now this representation is a single agent. Now we have multiple agents. So now we're talking about something maybe you could model with an agent-based model, or in this case, a 2-dimensional flow field. And so all dots here that you see are sort of begin in the center of the field, and then they evolve outward with respect to time. They diffuse in some way. And we haven't really worked out the dynamics of this. The idea is that they would diffuse, but what's it based on? Is it based on their attributes, their internal attributes, or is it based on some universal flow field attributes? What is going on? How do we actually represent, and then how do we link it to processes in the cultural world? That's the thing that's really the key here. And it looks very abstract right now. It doesn't really seem to fit, but we get these sort of vortexes and ridges. At least we predict that that's what we'll see, and those represent different patterns or even structures. And so the idea is, you get these heterogeneous ridges with different, agents that have different representations. We color code the different representations here. So, we expect things to cluster by like representation or different representations. That's what we mean by homogeneous versus heterogeneous. But this, it's kind of hard to map this to like actually what's going on in the cultural world, but it's also hard to figure out exactly what mechanisms we want to use for this. So this is something that's been hard to really kind of represent well, but I think this is like conceptually the right direction. I wanted to talk about integrative communication between automata. So you can have pairwise relationships between automata, and I wrote a paper here on contextual and structural representations of market-mediated economic value. So these are like agents that are trying to form value for certain objects, and they're actually assigning economic value to them. The idea is that, economic value is actually this sort of symbolic activity. It has meaning. It's polysemantic. In other words, you can have multiple meaning. You can have multiple values for something, where you can have a value that fluctuates with the meaning of the object. Some objects could be very useful or very valuable, and like you think about the art world. People paint works of art. Sometimes they're really highly valued, but they're just look like trash. Their component parts might not be worth much. But when you put them together in a certain way, they come out as this great work of great value. Similarly, in some cultures, like diamonds or gold have different values. So, it might be very valuable in one culture, maybe not so valuable in another culture. So there are different ways to look at objects in the world in terms of their value. In this case, it's economic value. And so, we thought about this in terms of pairwise comparisons of agents with different specialties, and then they randomly exchange resources or retain resources. And then this is what information favors trading or retaining. So you can model trading, retaining, and then look at the value of things over time. And so this is based on economics in nature, and it's a model by Noe and Van Hooft and Hammerstein. And this is a economic model, but it's also based on the CGS agents. Finally, I wanted to talk about ecological CGS. So now we can think more explicitly about ecological anthropology or ecological ecology, or cultural ecology, I'm sorry. So how does culture adapt to its environment? And so this approach is inspired by cultural ecology, but also ecological anthropology more generally. And so in our case, we think of a population, we think about how it needs to evolve in terms of culture. And it evolves in maybe a couple ways. It's not as straightforward as you would think. Population, of course, has to adapt to their environment, but they do so in different ways, and there are costs and benefits involved in these. So in this case, they're kind of working with the environment here. They're building a house, and it's kind of embedded in the landscape, and this has properties where it's good for heating and cooling. And so I don't know if you've ever seen this, but they build houses like not necessarily underground, but like as like part of a, they put earth over it so it insulates the house from the elements. In this case, someone's going out and exploring the desert, but they're driving in a Jeep. And so the Jeep actually is a lot of ecological costs, but it allows you to explore the desert in somewhat comfortable settings. And so each of these things are maybe more or less, this is maybe less sustainable than this. It might enable people to live in a certain environment. It might allow them to explore the environment. There are different costs involved. So there are all these things that are involved. It's not just a matter of looking at what's most efficient. We think about like a maximization perspective. We think, well, our culture has to evolve to, maximize its utility or maximize adaptation. But those things are often very hard to grasp. And so this is an approach where we use genetic algorithms to look at these. We give each agent a genome. So we give them this particle genome. So each agent is a particle. We give them a genome. Gives them an identification in terms of their lineage of origin. You can mutate this so that it matches either like a cultural lineage, I wouldn't say a cultural lineage, but like it changes, you can change your cultural lineage based on mutation. So, if you change your mind or if you change your practice, you can join a new lineage. And then there's a sequence that involves gene and environment interaction. So there's like an innate attribute to this. And so we have conditional diversity and survival. So the state defines lineage and identity, but also is used to assess the homogeneity of these coherent structures, or these clusters of cultural practice. So in other words, like, if you have a bunch of particles, a bunch of agents that are clustered together, they, was their origin from the same sort of representation, or did the representation change to favor like one cluster over another? So if I, start out at a different point, we started at a bunch of different points, right? Are there certain cultural practices that are so good that they, lead to this one, that there are a bunch of agents that converge to this one place? And then, of course, there's survival. So depending on your innate features and then your environment, like in general, very general relationship of culture, where you have, you have needs, like you need to wear, if you are a human and you live in the far north, you need to have a lot of heavy clothes. And we don't have the ability to evolve like, some sort of thermal regulation that would match the environment. So we need to have cultural attributes that help us. And so that's what this is all about. And so we weigh this, changing our cultural practices against this gene and environment interaction part. I've just sketched this out as like a representation. This is not the way it has to be. This is just the way it's been proposed. It can change quite a bit because this is very, I don't know what the utility of this representation is necessarily. But you can see that you have this diagram where we have these particle genomes, and we load them into the agents, and they diffuse across the space. And there's a representation of like a genetic space here, but it can be whatever you want it to be. And they diffuse into different locations. So, we're thinking about this in terms of like, different metaspaces. And, it's, again, that can be, we can think of how to best do that. And so flow conditions act as selection. So there are flow conditions in these structures. It could be uniform. It could be like favoring one thing over another. The particle diffusion acts. These particles diffuse at a certain rate, but they encounter these flow conditions, which affect their evolution. But then they're also mutating, so that also affects their evolution. And then coherent structures are these things that form, that define sort of the mean boundary of, the population. What's the total range of sort of adaptability here? And it would be represented by all these clusters. And, obviously from this example, we're not evolving anything going in this direction. It's only kind of in this direction. And so, these are like, this gives you sort of a spatial cast to your models. You can look at it either in terms of like geography, or you can look at it in terms of genotypic space, or you can look at it in terms of some other space that's important to you. So this is very flexible. And I think that's it. So thank you for watching this presentation, and hope you found it